What is up, everybody, and welcome back to another video. This is how to invest. This video will be on QuantumScape again because I got a pretty good amount of interest from the last one, so I figured I'd go a little bit more into depth about what they are trying to make and the technology that they are trying to innovate. So as always, let's hop right into it. Here I'm just on the QuantumScape website. This is what you'll get if you open it up. This is the home page. And I'm just going to go and click the solid state battery landscape. There were a couple things that I wanted to talk about. So firstly, we will start at the diagram. So this is a typical lithium ion battery. If you do not know this, well, if you did not know, this is what it looks like. This gives you a closer look, kind of a microscopic, because these are microns. I think most batteries are about 10 microns, which, if you know that source of measurement, is pretty darn small. We can see here there are 5 major parts. So there is the cathode collector for the current, and there is the electrolyte and the active material, the separator, which is what the biggest part that QuantumScape will be trying to innovate, and then there is more material. This is liquid electrolyte, carbon, silicon anode, and then the anode current collector, which is usually made out of lithium. So what QuantumScape is trying to do, or what has already achieved, is cut out a large chunk of the conventional lithium-ion battery, which has been around for decades. So, like I said, this is the previous diagram. They are trying to get rid of the carbon and silicon anode and just have the current collector. So as the current runs through the cathode active catholyte, it will go through the separator, which in QuantumScape's case is solid instead of a porous material like most would be in the current lithium-ion batteries. They would either be made out of a liquid or a gel or just a somewhat porous material that is easier to pass through than a solid separator, such as ceramic. One good thing about ceramic, which there's numerous good things, is that it can be cheaper, because I know that some of the other materials that they use are either carbon or either metal-based, and which are much more expensive than what ceramic would be. So what are the benefits of this? This causes the battery to not only be smaller in size, which is good for cars because there's only a limited amount of space, but it also increases the energy density that is allowed to pass through the battery. And they will get more into that here. So the promises of solid-state lithium-ion battery: energy density. Since carbon makes up the anode and takes up space and has mass, eliminating increases the energy density of the cell. Power density, fast charge. These will be able to charge much faster than normal batteries. And the cycles through the cell into the anode that has to diffuse the carbon at a rate that is governed by fundamental properties of graphite. Any attempts to drive lithium ions into the carbon anode particles faster than natural rate of diffusion and can result in the lithium plating on the surface of a particle instead of diffusing it, causing it to capacity loss and failures. Eliminating the carbon removes this limitation, allowing the fast charge without any adverse impacts. So that gives you a little description on how they will be able to charge faster than current state batteries. The cycle life of the cell is partly limited to by an irreversible chemical side reaction at the interface of the carbon particle and the liquid electrode, which consumes a little bit of lithium on every charge. So there is a slight runoff of energy, resulting in cumulative loss, like I was saying, over the life of this is just degradation, just the battery losing its maximum power over time. With no carbon in the anode, this side reaction should be eliminated, resulting in improved cycles for cells. So this means that the batteries will be able to last longer and essentially for a car have more charges without losing mileage on your total range, which is great for EVs considering that, especially currently, the infrastructure for charging is really not the best. We are kind of looking a couple years out on really building that up. Safety, the polymer separator and the liquid electrode used in the lithium-ion batteries are both hydrocarbons and combustible. Starting a fire requires these three elements: a fuel, oxygen source, and heat source. Because the electrolyte, a fuel, is in direct contact with the cathode, which is an oxide, the only other element needed to cause a fire is a heat source. Many abused conditions, from an internal short circuits to accidents, can provide that heat source. Replacing the polymer separator with a solid-state ceramic separator that is thermally stable to very high temperatures and does not burn both reduces fuel content of the cell and provides thermally stable barrier between the anode and the cathode. So this is just saying that when the lithium-ion atoms are traveling from the anode to the cathode or vice versa, that it has little to no chance of causing an adverse reaction due to heat because of the just the good insulation provided by the ceramic compared to other materials that are being used in the industry today. And the cost, this is one I kind of already mentioned, but ceramic is much cheaper, and anytime you can cut down costs, including on the anode, just getting rid of all of the liquid and the substance in there is great for the company. Some challenges, these are the three main ones. The conductivity, they just need to be as efficient as other batteries today. They need to be chemically and electrochemically stable, which it seems to be currently, and resist the formation of lithium metal dendrites. This is kind of the main one, in my opinion, because they seem to already have the power there, and they seem to have the stability down. It is just dendrites, which we've talked about in the last video, but if we look at a diagram, the QuantumScape batteries will not have this section right here, but when the current is being sent back through the anode, it kind of gets pushed through the wall and splits out kind of like a tree with no branches, and that is just bad for the battery, causing many short fuses and can even eventually ruin your battery in the short term. If we wanted to look through here, this is some of the materials that are currently being used in the industry or what are other being tested. Polymers, so these are polyethylene oxide, which were initially thought to be a candidate for a solid-state separator. Unfortunately, they're generally deficient on all three of these requirements. So we don't have to read any further. Not really worth it. Sulfides. The discovery of lithium-conducting sulfides such as LGPS by a professor in Japan over a decade ago generated excitement because they were thought to be highly conductive, addressing one requirement. However, they are among the most thermodynamically unstable. Right? So it can't complete at least one of them, so you have to move on. Oxides. Lithium conducting oxide separators were discovered over the past few decades, but have some been oxides have sufficient conductivity, which is good, and stability, and conventional oxides too have been unsuccessful at suppressing dendrites. So that is kind of where the issue is there. If you're getting a bunch of dendrites, it's not really feasible to be using that. Composites, some groups have worked on composites consisting of polymers and ceramics, so a combination. The best of both worlds, which using the hardness of ceramics. Unfortunately, the worst of both worlds is what actually occurred, so kind of tough luck for that. And then the last one, liquids. Some groups continue to work on conventional liquid electrolytes, but these efforts still challenged by the twin problems of dendrite formation and the impedance growth of chemical side reaction, so degradation. The important note to the system using any foregoing separator materials is still possible to make cells, but cycling has to be done under compromised test conditions. So a carbon or silicone anode instead of lithium metal, low current density, elevated temperatures and pressures, low life cycle, excess lithium on the anode. These are our key questions, and then here is a chart that I would like to get into, kind of quantifying the current data of companies that are testing solid-state batteries. So if we look here, the numbers, good numbers will be in green, average is in yellow, bad is in red. If we look up here, these are the companies involved. The first column is the separator, so what they're using to separate the two different current collectors at the cathode and the anode, and what they are using as an anode for the material. These are the number of layers that they currently have. Cycles just means the amount of times you are able to charge the car. Well, the battery, but they would be going into cars. The density of the battery, and the temperature, and finally the pressure output. So if we look at Toyota, they are using a sulfide, which if we look back here, we can tell that it probably won't be successful unless they are able to further advance the technology of sulfide separators, because they're quite limited in their current state. They do not have a lot of available data published, I think because they are kind of weak data, and I don't think they would be wanting to put out such bad numbers, which may be why they just did a deal with Tesla. So maybe they are trying to get in some of their batteries, which I know that they are provided by Panasonic, which is not listed on here. If we go to the next one, Prologium, this is the combination, so either the best of both worlds or the worst of both worlds, and they do not have a lot of data published, but the one number that they do have is 1,300 cycles, which we will do some math on in a minute, but it doesn't really make sense just to put out one number. It kind of is just saying, hey, we're picking and choosing our data. Why would they not put out any others if it was good? Because obviously this is a really good number. So if we look at the amount of cycles, 1,300. If we look at average range for a electronic vehicle, it's probably 350 miles. You have a battery range of 450,000 miles. So that lasts quite a bit longer than most batteries on the road today in ICE vehicles. But considering that they are not publishing the rest of their numbers, I would not be too inclined to be bullish on this number. If we look at ionic materials, they use a polymer, and they also use lithium, just like QuantumScape. So now we're looking at all lithium anodes. The reason that people would use carbon is because it kind of eliminates the possibility of dendrites, but at the cost of energy density, which is kind of why they don't have these numbers published, because it makes the batteries much less efficient in putting out power, but safer because of dendrites, which is kind of a cost that they are paying. What QuantumScape is trying to do is have the best of both worlds by eliminating the effect of dendrites and trying to eliminate them and have the energy density. But if we look here, they only have one layer, which if we look, the automotive requirement is dozens. And when I hear dozens, I would imagine 2 to 3, so 24 to 36 different layers of batteries, which are not very big. They're about maybe the size of a playing card, is what the CEO of QuantumScape said, and they have a really good hour-long presentation, kind of going through a little bit what I'm going through, but their investor presentation, which I would be more than happy to go through if you guys would like. I've done investor presentations before, but It is very, very, very small, much smaller than you'd imagine. And to get up to a dozen layers, he said that it would be about the size of a full deck of cards. So the battery is much, much smaller than batteries today, hence the density. But this company only has one layer, and that layer can only be charged 20 times. So still pretty far away. If you multiply that out by the average range, you can tell that you probably wouldn't want to buy that car or battery. The density is below standard. You can see that it has to be greater to or above 3 to be able to be competitive on the market today. And they actually are competitive on the temperature. They do not overheat, which is a good thing, but they have not published their pressure, which probably means that it is not up to standards. If we go to Samsung, they are using a sulfide, which is another material that was listed as one that probably would not work unless further engineering and ingenuity were to occur. Now, they do have 2 layers, which is kind of, in my opinion, the most difficult thing to do, add on to 1 layer. Once you get the additional of 1, you know you can do it, and you just have to add additional without losing efficiency, which is easier said than done. But they have 2 layers, 1,000 cycles, which is quite good. If you multiply that out, 1,000, it's about 350,000. So much longer than most ICE vehicles last anyway. And the driving density is 3.4, which is actually the most on the list. So props to Samsung there. But the temperature is too hot as of late, and the pressure is way too high. Now, some of these data points may be a little out of date, but these are the latest numbers that we have to work off of. Whoops. We'll go back. I accidentally clicked on the source there. If we go to the next one, it is SES. They do not have the numbers of layers published, so I wouldn't really take this too seriously, because if we don't know the layers, then it doesn't really mean much. The cycles is 60, which I don't know why they'd put that out there. That's not a good number. And the density isn't good either. So I don't really know why they're publishing data. I guess it's better than nothing. But to each his own. Solid state power, they are also using a sulfide, which we have read that faces major challenges. They have 22 layers tested, and they also have 2 layers. Now you can see that they have positive and negatives on both batteries, because obviously you can see here the cycles on the 2-layer battery is much better. You can see the degradation is very bad at 30 cycles, so you can only charge the battery 30 different times after using it. So if you get a car and you can only charge it 30 times, you'd be pretty pissed. And they only have 0.3 energy density, so these are not dense. They are much bigger batteries than QuantumScapes. I'm imagining that they would still have the anode materials and fluids running through it, so that is about 1/3 of the battery added to it. And they are under temperature, which is a good thing. So we did not to overheat and cause fires or short circuits. And they have not published their pressure. Now, if we get to QuantumScape, obviously this is going to be biased, because they are putting together this presentation and they have the most up-to-date information on their own company and they don't on the rest of them, and they are trying to sell themselves, but we will go through here. So just as a month ago, they released that they were able to build a multi-layer battery going from 1 to 4, and they have minimal degradation. It's still about 1/5, so 20%, but something that could be worked upon. If they can get up to dozens, they would just have to work on the efficiency and the loss of range over time. The density is up to standards. The temperature is up to standards, but the pressure is slightly high, and they are the only ones who are posting this besides Samsung, and Samsung is way above QuantumScape, so they are kind of way ahead of the game in all of these numbers. So the one thing that I wanted to look at was the degradation numbers. Now, you can see here a fifth is nothing to scoff at and something that I would consider non-negligible. But if we look at the interview from the CEO, we will see what he has to say. As you can see there, he said indistinguishable, essentially indistinguishable. I would not consider 20% is essentially indistinguishable. I think he is kind of overselling it and overstating what they have currently produced right now. Take that into account as you may like. These are just the facts that are out there. So that will be the end of the video. If you made it this far, definitely subscribe, give a like. It's definitely much appreciated and helps the channel grow. As I said in the last video, I will be having my Robinhood and Webull links posted in the description. If you did not already subscribe to either of those brokerages, you can get some free money. Can't talk there. So definitely check it out. And thanks for watching. Have a good one.